Now we know that we can describe the reflectance properties of any material found in the real world using the BRDF representation. So now let's take a look at some BRDFs or reflectance models that are very commonly found in the real world. But first, let's talk about the main mechanisms that produce reflection. The first is what we call surface reflectance. You have light falling on the surface, and the reflection takes place at the surface itself, the interface right here. The light is reflected. And so this is also called specular reflection. It gives objects a glossy appearance or shiny appearance, and it mainly comes off of smooth surfaces like mirrors, glass, and polished metal of different types. That's surface reflectance. And the second mechanism is where you have a part of the light actually entering the material itself. It goes underneath the surface, and underneath the surface you have these little particles that are made of different things, because typically materials are not homogeneous. They are non-homogeneous, and you have particles made of different things, which means that they have different refractive indices. As a result of which this light that enters gets refracted and reflected multiple times as such. You see the light bounces around inside. I'm showing this as going pretty deep here, but this happens at the skin of the surface, a very, very small depth with respect to the surface itself, bounces around, and this is such a random process that ultimately when it makes its way back to the surface, it gets scattered in many different directions. And that's called body reflection because it enters the body of the surface, the material. So body reflection is also often called diffuse reflection. It gives objects a matte appearance, and it's because of the non-homogeneous nature of the medium itself. So you're looking at things like clay and paper and liquids of various type and so on. So in general, when you look at the intensity at a point in the image, it's of course the result of reflection from some point in the scene, but that intensity, you can say, it has a body reflection component and a surface reflection component in general. So let's take a look at a couple of examples here. So here is a clay vase, and you see that it primarily has body reflection, meaning to say in this case light actually enters the surface and then bounces around, comes back out, and it's sort of distributed widely in terms of directions, and therefore it has this matte appearance to it. On the other hand, you see here a surface reflection or specular reflection. That is, there's no light really entering the surface, the body of the object. It's all being reflected at the surface itself. It's mirror-like reflection. But in general, one can say that you have a hybrid of these two mechanisms, and we'll call that hybrid reflection, which is a combination of body and surface reflection. So in this case, you have, from your vantage point, you have primarily body reflection in this area, but here you see there's a combination of both body reflection and surface reflection. And therefore, you see this highlight that's sort of sitting above your body reflection. You see highlights here as well. That's a highlight, that's another highlight, but underneath that you also have the body reflection itself. So now let's take a look at some commonly used reflectance models. Let's start with the Lambertian model for body reflection. This is due to Lambert, 1760. And what's interesting about this model is that it essentially states that a surface appears equally bright in all directions. It doesn't matter which direction you observe it from, it has the same surface radiance. So in other words, its BRDF, F, is a constant. Rho D, D for diffuse, rho is albedo divided by lambda. So rho D is called the albedo, which goes from 0 to 1, 0 for a perfectly black surface and 1 for a perfectly white surface. The perfectly white surface essentially reflects all the light that it receives. So this is very commonly used in computer vision and in computer graphics, partly because of its simplicity, but also because it actually describes, at least approximately, a variety of surfaces found in the real world. So let's take a look at the relationship between surface radiance and irradiance in this case. So we know the BRDF is L divided by E. So L is equal to rho d divided by pi times E for a Lambertian surface. And we know that the irradiance, right here, we know from our radiometric concepts that the irradiance is J cosine theta I. Theta I is the angle of incidence right here, divided by r squared, the distance of the source from the point. That's the definition of irradiance. So that's J divided by r squared. Cosine theta can be written as n dot s. N is the surface orientation, unit vector in the direction of the surface orientation, and s is a unit vector in the direction of the source. That's right here. So you have n dot s. So in other words, you have L equal to rho divided by pi, J divided by r squared, n dot s. Now remember that J is a constant, rho is a constant, depends on the surface, the material property, and r, let's assume for a minute, is also constant, meaning we want to understand what happens when you move a light source around a Lambertian surface, but holding the distance of the source from the surface the same. That's r right here. So imagine first that you illuminate the Lambertian surface from the top, meaning that theta I is equal to 0, therefore n dot s is equal to 1. You get, of course, equal radiance in all directions, because that's what a Lambertian surface does, and it's pretty bright in this case. But if you increase the angle of incidence, that's increase theta I, again, you get equal radiance in all directions, but the radiance value itself drops, and you can keep going that way. As you get closer to the grazing angle, the brightness of the surface drops again and then approaches 0 as theta I approaches 90 degrees. That's a Lambertian surface. Here's an example of a Lambertian surface. If you look at this face right here, it's not possible for me to show you this, but if you moved around this face, you'd see that it appears equally bright. The only reason its brightness changes is when the illumination direction changes or the irradiance changes. So the Lambertian model really represents one end of the spectrum. It is body reflection, and an ideal form of body reflection in some ways. It says that it doesn't matter what the illumination is, the surface always appears equally bright from all directions. Now let's go to the other end of the spectrum, and that is an ideal specular surface. This is the ideal specular model. In this case, what you have is mirror-like reflection. All the reflection happens at the interface itself, so it is surface reflection and not body reflection. And all the energy of incident light is reflected in a single direction in this case. So here you have your setup, you have a source, you have your specular surface right here with surface orientation n. If you illuminate it from the direction s, then it reflects light in one and only one direction, which is r, which is called the specular direction. And this vector r is a reflection of s about n. So in this case, the BRDF can be expressed as the product of two delta functions. So the first delta function essentially says that the two zenith angles must be the same. The second delta function says that the azimuthal angles must be the opposite of each other. So it's phi I plus pi minus phi r. And then in the denominator here, you have cosine theta I, sine theta I. This is actually a factor of proportionality, if you will. It's just making sure that the law of conservation of energy is being satisfied in that the light that's reflected over the entire sphere, irrespective of all the directions, is equal to the light that's received by the surface. So that's where this comes from. So in the case of an ideal specular surface, the viewer receives light only when V, the viewing direction, is equal to R, the specular direction. So let's take a look at how these things manifest visually. Let's first take a look at the Lambertian model, which is body reflection. Let's assume that you're looking at a sphere, which is Lambertian. And the viewing direction is V, and the source direction is S. Even though I've shown the source and the camera very close to the sphere here, let's assume that they're actually really far away at infinity. And the angle between them is theta. So now you see here, this is the image that the camera ends up seeing. And in this image, the brightest point is this point right here, where the angle of incidence is equal to 0. You know that for a Lambertian surface, it's going to be brightest when the illumination comes from up above, direct illumination. So that point is the brightest, and then it falls off from there. And then you also have these isobrightness contours on the sphere, which have equal brightness because the angle of incidence for each one, along each one of these isobrightness contours, remains the same. Okay, now let's take a look at the other extreme, which is your ideal specular surface. Again, you're going to assume here that the camera and the light source are really far away. So the direction is V, the direction of the light source is S. And in this case, the camera observes a reflection, non-zero value, only for one point on the sphere. And that point corresponds to this point, Q. And Q has a surface normal, which is a bisector of V and S, because that's the point for which the angle of incidence is going to be equal to the angle of reflection. And that's the only point in the sphere for which that's true. So you get a bright point right here. So these are very simple models, but very widely used, because we know that we have very shiny mirror-like objects in the real world, but we also know that we have very diffuse, matte, Lambertian-like objects in the real world.